It's 50
45.
minutes. It's up to you. Essentially, this is really your
I see.
your take of how you want to do it.
Right. About 40, 45 is
It's 50
45
minutes.
about the right. That's as much as, somebody, yeah, they have their attention.
Exactly.
After that,
Exactly.
it becomes intellectual overload, right?
Exactly. No, but this one, there, the nice thing is that most people are fresh. I know they're actually just
That's great.
on the thing at the moment, so this is okay. They're actually awake. Most some of them are in the morning in the US as well. I know
see.
Mark comes in the morning, but I think he's working out while he listens or something like that. So
I see.
I try to put him at sometimes on the panel, but he refuses.
I see, because he's
All
all
them
in
in the
deep mode.
pajamas, they're like having their coffee and listening to a seminar in the mornings. It's also quite useful.
I see.
Okay, okay, we're now on time. So let me start and welcome into all the guests in here coming in. Welcome to the online SPICE and SPIN+X seminar that I lead here together with Libor Schmekiel and Jela Wittmann and Karen Eberso-City, and in collaboration with the SPIN+X Research Center, a collaborative research center led by Martina Schliemann, Burkhard Hillebrands, and Matthias Chloe. This is, as you guys know, it's a webinar format, so you will hear the speaker and the people promoted to the panel. But please feel free to write questions either in the chat or in the Q&A, or raise your hands, and I will promote you to ask the questions. So this is I'm very happy to welcome Kerem Çamsarı. He is a professor at the University of California. He actually was a Hoosier. He graduated like me from Indiana, but from the different university in Indiana. I was more south, he was more north. And then he works and established a lot of work connecting to the emergent materials from phenomena and circuit systems, particularly exploited lens for type of brain-inspired ideas of how to go beyond more in this new era of electronics. And he has a long list of awards that I, very impressive ones. Bell Lab Prize, I'm not sure what I haven't heard of that one before, but anyway, we're looking very much forward to your talk. You can go ahead and start sharing your screen. Okay. And yeah, I'm gonna.
All right.
Thank you.
Yeah, thank you very much, Professor Sino. I know many years ago I came to Germany and was part of this, SPICE, as many of you know, these wonderful seminars over the years, and there we were just starting out, and I was in one of those workshops, and that talk is also online, and I know that many people have watched it. So it's great to be back this time online. But I'm hoping to tell you a little bit more about what we've been up to on this field, which we call this probabilistic computing with p-bits. And I'll try to show you how that's applicable to all sorts of things. And we're very fortunate to receive some funding in this area. And it requires, let me tell you, there's a lot of experts or practitioners in the audience. It's an exciting field with a lot of things across the stack. So a lot of you could help in identifying, better p-bits, better problems. There's physics, electrical engineering, circuits, devices, even computer science. So it's an active field with a lot of interest. So I'm also hoping to engage and stimulate some of you so that you can continue work and make this field bigger, because this is, we believe, beyond p-bits. Okay, I have, over the years, I have a lot of collaborators. As Jairo mentioned, I did my PhD with Supriyo Datta at Purdue University in Indiana. And during our postdoc, this is when this field kind of, at least we started to work on this field. And I also work closely with Professor Shunsuke Fukami and Hideo Ono and Shun Kanai at Tohoku. And I also have European collaborators like Giovanni Finocchio. Some of you will be familiar with his work in Spintronics. And I have some wonderful graduate students. So these are my longtime collaborators over the years. Okay, so let's, I think, dive right in. And, you know, we are all familiar with bits, basically. You know, everything runs on bits. This is this abstraction that you have a logical 0 or a logical 1. And this abstraction, we build it using transistors, right? As all of you are familiar. And the idea of the bit is that it's this very deterministic 0 or a 1. In fact, that's its strength, right? It makes it very, very robust. And you can put billions and billions of devices, transistors, on these chips, and you can exploit this binary nature of bits, and everything runs on bits, right? You know, ChatGPT runs on bits. Everything that basically powers our modern life is based on the bits. And you know, you note that, you know, you see that. Let me get a laser pointer here. So CPUs, GPUs, and TPUs. You know, I don't know the latest number, but now maybe it's close to 150 billion transistors. Right, and on the other extreme, you have qubits, this quantum bit, and quantum bit is very different, right? It's in some sense a different object where even just to describe it, you have to. I often say that you have to, you know, incorporate this technical term. You have to say that it is a superposition of 0 and 1. It's not just 0 or 1. And there you know, invoke some discussion. Is it really 0 and 1 at the same time? Well, not quite, but it's in a superposition state and so on, right? And there's worldwide activity. It's still ongoing, especially from the big players like Google's, IBM's, and Microsoft's of the world. And they're trying to build hardware for these qubits. Now, these are two extremes in some sense. You know, bits are as classical as it gets, and qubits is as quantum, as fundamental as it gets, right? And in this, if this was a spectrum, you would expect to have something in between, and that something would be probabilistic, right? Because quantum, as you all know, is first and foremost probabilistic, but it is more than probabilistic. It is phase coherent, and it has this wave function and so on. But it's first and foremost probabilistic. So as you go from bits to qubits, it isn't unreasonable to expect that at some point you would traverse the land of something that's purely probabilistic. And that's what we have, you know, set out a few years ago to understand the qubit. Actually, how do you, in what situations do you need the phase coherence, and how does it help? And we've introduced or you know, popularized this idea of the probabilistic bit, which fluctuates between logic 0 and logic 1, right? And the other point I often make in this point is, if you look at the, you know, state of the art in bits and qubits, you will see that things are becoming domain specific. Things meaning hardware isn't like the good old days where it used to make everything better. Now hardware is becoming specialized. For example, you're building GPUs and TPUs for ChatGPT, for machine learning applications. And even in quantum, you would still work on some niche problem. For example, maybe simulating quantum mechanics, solving some quantum magnets, ground state, or electronic structure, quantum chemistry, whatever it is. These two areas are becoming domain specific, that they're not going to replace everything else. Now, this p-bit, when we set out, this is also exactly the same philosophy. You're not going to use this for purely deterministic problems, and you're not going to be able to use this for completely quantum problems where you need that phase cancellation, you need the quantumness of that system, right? And you know, two very active fields in bits and qubits are these machine learning and noisy intermediate scale quantum computing. That's NISQ era quantum computing. And I'll show you that with p-bits, you can sort of overlap in terms of the applications of these two things with good examples. So what are those good examples? Well, as I mentioned, this machine learning and AI, if you look at that field, you find that there's a lot of physics inspiration. For example, they have these, I mean, the simplest thing that you can think of that, and you can argue is physics inspired, is the idea of true random number generation, and in the sense that massive true random number generation. In fact, later in a few minutes, I'll show you examples where the system is going to need, let's say, 1 trillion random numbers in 5 seconds. So when I say, often when I say random number generation, what I mean is this massive requirement of randomness for a probabilistic algorithm or an application. And that's usually, you can imagine this being physics inspired because, in physics, we have a lot of random noise and we have a lot of, systems with entropy, and you can go and use that, et cetera, right? And maybe a little bit more sophisticated, if you allow correlations between these random units, those nodes, then you end up with what people call these energy-based models. And energy-based models are now, as an alternative to this modern paradigm with deep neural networks, they are becoming very important. People are still trying to fundamentally change the narrative on some of these modern deep neural networks, and they look to physics for inspiration. And there's a lot of energy-based models. Some of them are, some of them are old, some of them are new, like Boltzmann machines, belief networks, equilibrium propagation, predictive coding. So things like this are becoming, drawing more attention. And with p-bits, whenever you have some physics inspiration and probability, then you can imagine building them. I mean, these become literally p-bits, the edges become some sort of connection, and then you can apply them to these problems. We have, several papers on this, but, you can find, I just put one representative paper there that for you to look at if you like. Now, another field that's becoming very active, now there's sort of national programs like DARPA programs, MURIs in the US, these large funding mechanisms, are these combinatorial optimization problems. Now, these are problems that are discrete, things like the traveling salesperson problem, for example. You're trying to visit a number of cities, you're trying to minimize your costs, or you're trying to solve some scheduling problem, a logistics problem. So you have a combinatorial amount of a combinatorially exploding number of solutions or possible states, and you're trying to go through these solutions so that you can find one that is practically useful, right? And there are lots of problems. And these are in this class of CS class of NP or NP complete, which means that nobody knows an algorithm. It's easy to check whether the solution is useful, like solving a jigsaw puzzle, for example. You can at a glance see that if a person solved it, but it's very difficult to solve them. It's believed to be very difficult to solve them. And these often we take, again, inspiration from physics, and they will have this energy minimization kind of idea where there's a landscape of possibilities, and then you bounce that ball around and you try to find the local minima or the ground minima as best you can. And these often require, as I'll show you later, probabilistic algorithms. Okay, and because one idea that many of you are familiar is the idea of getting stuck in local minima and then having noise kick you out from there, and then it gets worse before it gets better type of idea that we also have in life, right? It gets a little worse before it gets better, and then you find better solutions. You hope to find better solutions. Now, this is very active, as I said, and p-bits are just, as I mentioned in the beginning, p-bits are just one approach to, or probabilistic is just one approach to attack such problems. There's a lot of activity both in Europe, Asia, and all over the world, actually, on trying to build physical computers to solve these problems more efficiently. Now, there's one more that is kind of understudied, and that's becoming, at least from a hardware perspective, that's becoming very, very important. And that's this idea of quantum simulation. Now, if, in the beginning, this may sound a little bit strange. You might say that, wait, I thought that this quantum and p-bit are completely disjoint sets. I thought that you could never be like quantum computers. Now, the answer is, it depends. It depends on the problem that you're trying to solve. And there has been traditionally two main approaches. Well, actually, until recently, there has been only one approach to solving quantum problems with probability, and that's this field of quantum Monte Carlo. Okay, and physicists have known this at least since the early 80s, where you can have a quantum system, and you can have a probabilistic system that maps to that quantum system, even though the probabilistic system is, doesn't have any phase, doesn't have any entanglement. You can map these quantum systems, at least certain properties, statistical mechanics of these systems, into these networks of probabilistic systems. And the technical term they would use is these replicas, right? So this is I have a picture here. You have a replica of a quantum network, and then you have many of them that are interacting in the vertical space. And then you can do Monte Carlo on this interacting space, and you can solve a quantum problem of interest. Now, where does it stop? Where does it not work? Well, there is this fundamental problem that's called, when you write this down, write your Monte Carlo algorithms. Sometimes if you're doing truly quantum systems, then you might see negative probabilities. And because, quantum doesn't care, but probability, our Boltzmann factors are usually positive. But when you do the mapping, you might find that, okay, suddenly I ended up with this negative probability. In those cases, this method becomes a little bit tougher to work with because we don't know how to deal with such negative or complex probabilities. Now, nonetheless, this quantum Monte Carlo has been very successful, and it kind of includes systems like the one that D-Wave is considering, for example. And I still find that anything that practical that you can do with a quantum system, quantum annealer in that context with D-Wave, you can do it with probabilistic systems. And if you put them on physical hardware, you can probably do it orders of magnitude faster and in bigger systems with less errors and so on, and without the requirements of extreme cryogenics. Now, in the last few years, there has been a big development in this area, right? And that's the idea of throwing machine learning at this problem. And they threw in 2017 or so, there was this idea of training none other than energy-based models, Boltzmann machines, or a form of restricted Boltzmann machines, to solve the many-body problem through a variational approach. Okay, so the idea is very simple. You say that, okay, your wave function could be complex, but in the end, you have a probability distribution. Because if I take a probability, if I do any observation, I'm going to have a probability distribution, and hence I can throw a variational approach. I can guess this, and this is very common, this is very well known to physicists. I can guess a form of your wave function, throw thousands of parameters into it, and then try to approximate your wave function by energy minimization arguments. I change the parameters in such a way that they reduce energy, and in the end, I will kind of end up with something that your system is doing. So you see, it's a fundamentally different approach. You're not trying to emulate the dynamics, but you're basically trying to do a reinforcement type, learning type ideas. And this has become very active, and it has, in software at least, and I'm told by some European physicists like Johan Mentink that this has become the state of the art in certain classical approximation in some quantum systems. And of course, that's very exciting because everybody runs these models in CPUs, but as I'll show you, you can build computers from the ground up to represent these systems and solve these problems perhaps better. So once again, this is another area that's becoming very important. There are more, okay, but I'm not going to bore you with it. There are more. You can talk about, Markov, that you can talk about Bayesian inference, quantum chemistry, quantum machine learning. You can try connections of p-bits to all the way into bit research and qubit research. But I think that gives you a rough idea of the types of things that we're interested in. So what is a p-bit? Let's start with that. Now, you can, if you're coming from the ML area, you can say that, okay, p-bits looks like a binary stochastic neuron, right? And the idea is the output is a binary number. It's either 0 or 1. So it's very, very digital. I put this thing digital. I say that it's digital. And then there's stochasticity in the update rules, right? So it's a kind of a system, unlike a deterministic system where in each update rule you put some random choice, random element. And of course that makes it hard computationally to build because suddenly every unit now has to have its own private random number generator, right? And this neuron is a term that's borrowed from ML, but if you're a computer, if you're a computational neuroscientist, or if you care about biology, then sometimes you might be offended by this word neuron here, because this is really a simple mathematical object. And the way it works is mathematically it's a Bernoulli number, it's a random number between, it's either -1 or +1 or 0 or 1. And then it kind of gives you this random fluctuations as a function of time. So until this point, it's just a random number. But then you allow this analog input or continuous input to change your output probability. Okay, so that's the sort of basic idea. You always have a random noise. Every decision is random, but the output is tunable by this analog quantity. And that tunability is what allows the correlation, right? Because now you can talk to someone. You can change your mind and still be stochastic and so on, right? And sometimes we sort of show it as in this picture where there's a continuous I sub I in the background, the input, and then you change it slowly and you observe the output. And if you take long time averages, then you see this hyperbolic tangent or sigmoidal behavior, which has that exponential Boltzmann factor built in, as I'll tell you a little later, right? And the important thing to note is over the years, the community has come up with all sorts of different p-bit hardware implementations. So far, I have not introduced any hardware. So far, this is the building block for the computational unit. But I've seen, and there has been exciting work with MTJs, which I'll talk about. There's diodes, for example, these single photon avalanche diodes. People have shown that you can use the Poisson noise for those to kind of build p-bit. Digital CMOS is another thing that he ran now that I'll show. And there are other things like mixed signal CMOS, analog ideas, other nano devices. So there's all sorts of ways that you can build this thing. And what is ultimately important is energy efficiency, scalability, connectivity, variations, and things like that. Okay, so that's the p-bit, but how does the computer look like? How do you build a computer out of this? Well, the way you do it is, here's a picture where you have, a local picture here. You are the receiver p-bit in this light bluish color. And then you have neighbors. And your neighbors are all asynchronous. That's what these Fs actually represent. These are different frequencies or time constants that your neighbors are fluctuating. So just like a natural system, everybody is doing their own thing. But before you receive, they become inputs to you. You weight them. You weight their inputs with some weights. And then that becomes an input to you. And then you make a probabilistic decision yourself. Okay, so that's the physical picture. And as I'll show you, this is asynchronous. I'll tell you a little bit more about what that means. And there are, equations that we write down. These look like discrete dynamical systems. These are coupled p-bits. And we have the first equation is the p-bit. There's that hyperbolic tangent. We take a sine function because we binarize it. And then this is a form of a synapse, which is this, if you will, if you accept that this has some biological inspiration, this is kind of like a interconnectivity where you take your neighbor's input and then you have a private bias that sometimes, you get all this input, but you do what you wanted to do anyway, for example. Okay, so that's a little bit like a social network, right? Okay, and there's good theory behind this. There's this ground truth, which is defined by the Boltzmann law. And in physics, if we have bidirectional connections, we often write down energies, and those energies are usually related to probabilities, right? And these are typically difficult problems because as we know that, even for a discrete system, you have 2 to the n possibilities. The phase space grows exponentially, right? So in fact, that gives you an idea of what we are trying to do, that we are trying to estimate this ground truth, this complicated Boltzmann law using our coupled dynamical systems, which isn't exponential, right? That's the goal. You're trying to simplify this calculation. Now, there's another important development I should tell you, and that is, this Jij MIMJ in the energy, or Jij MJ, which is the derivative of this energy with respect to MI. Okay, the local field is usually the derivative of the energy with respect to MI. This is the so-called Ising model, okay, or Ising model, if you want to be, if you want to be precise. But you look at this energy and you say, if you haven't seen Ising model before, you could say that, why did you stop at Jij MIMJ? You could have done higher, you could have gone bigger. And that's precisely what this community is doing. they can, they notice that you can imagine more complicated energies beyond Ising models. And you can have, for example, Jijk, a third order tensor now, Mi, Mj, Mk. Okay, so this would be in physics a k-local or 3-local interaction. And it's a strange thing, but it can be, it's mathematically allowed. And it just, you see, it doesn't change my architecture. It only changes what is in that gray box. Previously, I was just linearly weighting. I had an affine kind of input to my p-bit. Now I can have nonlinear things. For example, I can have Ji, Jk, Mj, Mk summations. Okay, so these are so what I'm trying to tell you is there's all sorts of generalizations possible, and this is one of them. And you might look at this and you might think that, oh, this has become now incredibly more complicated. How would you put this on hardware ever? It's going to be a mess. Well, not really, because p-bits are 0 or 1. So this Mj, Mk multiplication is not really multiplication. It's basically like if Mj is 0, then you don't get the weight. If both of them if both of them need to be 1 for that Ji, Jk to enter into the summation. And that really eases this so-called multiplication operation. Okay, and once again, there's in lots of communities, there's a lot of interest in going beyond Ising models because they put more computation to the synaptic operation, allowing more complicated things to happen. Now, what is the main motivation? I've already talked about this briefly, so I'll be quick on this one. We try to do in the p-bit business, we try to accelerate this Markov chain Monte Carlo algorithm. Okay, Markov chain Monte Carlo is this very, very fundamental Monte Carlo algorithm, and usually the idea is to approximate that Boltzmann law. Okay, so for example, if you have two states, if you have two p-bits, then you have 4 states, right? There are four states to consider. They could be up, 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 down, down, up, and down, down, right? But as you increase the number of p-bits, then at some point, if this looks like a nice skyline in New York or whatever, and at some point you stop drawing these histograms because it suddenly doesn't look good anymore. Because with 8 states, you already have 256. With 8 p-bits, you already have 256 states, right? So you can see that this 2 to the n, and each of these probabilities are described by an energy whose exponential gives you a number that is proportional to that probability, right? So this is a very, very difficult thing to get right if you're trying to find the ground state or if you're trying to sample from this state, right? So that is the main motivation of building a physical computer that does this for you. And Feynman is famous for creating quantum computing, right? Like starting the field. In that very paper, Simulating Physics with Computers, you can go and see that he actually starts with a discussion on probabilistic computation. He says, if you're trying to simulate a probabilistic nature, use a probabilistic computer. That is the exact same idea of building quantum computers. If you're trying to simulate a quantum nature, use a quantum building block, use a quantum computer. Right? So we take a lot of inspiration from that. Now, let me make another important point here. And so I know some of you are physicists and all sorts of, you look at this Boltzmann law and you say that I've seen that before. I'm going to throw mean field at it. I'm going to throw loopy belief propagation and all sorts of approximations. We've played around with these things to train neural networks or to solve real problems, optimization problems. And we find that in trying to tame this 2 to the n exponential, we found nothing better than Markov chain Monte Carlo, which you may argue has some deep computational implication, which is you really have to put enough effort to kind of tame this 2 to the n computation. But mean field theories and things like loopy belief propagation gets you somewhere, but they don't work just as well as doing the probabilistic system and letting it evolve. Okay, and that's this idea of letting physics do the computing. We've been talking, we've been going around this idea. So let me show you a quick, pretty picture before I show you our real computers. So this is a interacting body system that we imagine, and you talk about these such things in classes in StatMech and so on, right? And I'd like you to sort of, I'm assuming there's more of a physics background in this audience, but to computer engineers, for example, this idea of asynchronousness, that doesn't come very easily because we've been building computers with digital clocks for such a long time. The idea that you can let your constituents in a system run freely, that seems like a very strange thing, especially if you're trying to do some deterministic computation. But in nature, that's what happens all the time, right? You kind of, everything happens kind of at the same time. And another thing in nature, interactions are local, right? That's the first thing. If this was a graph, you would have local connections. That graph would be sparse. This thing in the middle, for example, would only be influenced by its neighbors. And this asynchronousness is very important, that things are free and they don't wait for anybody. And because they are free, there is massive parallelism. What that means is, in a very concrete sense, you increase the number of p-bits, your performance will increase. You increase the number of the particles, your collisions will increase, right? And this is exactly how we try to build our architectures. These three things: sparse connectivity and asynchronousness, leading to massive parallelism. These are what are really important in our hardware implementations. Now, let me show you some state of the art, okay, where we are. Now, in 2019, using that same exact architecture that I've shown you, in sparse connections and in asynchronous interactions, and there's a synapse that's kind of being controlled by this at the bottom. It's a feedback system, right? We used stochastic magnetic tunnel junctions with Tohoku, and we've built an 8-bit physical computer. We said that, look, this stochastic magnetic tunnel junction gives you noise for free, so you could use that to solve optimization problems using these Markov chain Monte Carlo algorithms. But, I often joke that, this experiment took at least a few years to get. And at some point, we wanted to go beyond 8 p-bits. Okay, this physical implementation is good, but what can we do with present-day technology? And there we, in the last few years, in my group, what we've done is we've used these programmable chips. They're called field programmable gate arrays. These are programmable computer chips, FPGAs. And we were able to put, 5,000 or so p-bits into this machine, and we could solve really, really hard problems. Now, I'm going to allude to this later, but I mean, just look at this, that we are using billion transistor FPGAs. They're full power, and we can only put 5,000 p-bits. In fact, after I started to work with FPGAs, my respect for what this MTJ is doing increased quite a bit, because it's really doing something complicated for free, nearly for free. So that's why, and even with the world's best FPGAs, we seem to be stuck around a number between 5,000 and 20,000, depending on other factors. But nonetheless, it was a big, increase. And we compared our stuff, our solvers with others, and D-Wave and other approaches, and ourselves in 2019. And we were able to solve this optimization problem much more efficiently. Now we saw that we could factor some very large numbers up to 32 bits, etc. That was already doing something very interesting. So this physics-inspired architecture is promising, right? And recently we've also explored ideas of heterogeneous architectures, where maybe you can, if random number generation is so expensive, maybe you can outsource it to this MTJ and you can give it to an FPGA. And these are the types of things we've been talking about in IEDM last year, and this year we're going to talk about a slightly bigger system. So these are also very interesting from a computer architecture point of view, that to be able to combine this nano devices with the existing ecosystem. That's where we can make a lot of impact as a community, right? Because the CMOS is very powerful, right? And sometimes in a cheeky manner, I talk about, can we define a probabilistic advantage or supremacy regime, right? And what that means is, can you do something with MTJ plus FPGA in this hetero systems that you couldn't do otherwise, right? And could you have a notion of probabilistic supremacy and advantage, right? And we are trying to, for example, put hundreds of MTJs next to an FPGA and solve some problem. And of course, this requires a lot of interesting interdisciplinary thinking. Okay, you have an algorithm, you have a problem, you have hardware problems. So it kind of goes across the stack from physics to systems, right? So these are the types of things that we're trying to think about at this time to scale out. But I also have a lot of respect for FPGAs, and we are trying to scale out FPGAs as well. And this is an interesting idea, which has its own challenges, which is, you know, if you can put 5,000 qubits to one of these FPGAs, maybe you can split a big graph. You can basically take a big graph and split it into pieces, and each piece can go to a different FPGA. And of course, these communications need to be fast. You need to do this properly. But we think of, you know, maybe going to 100 or 250,000 qubit networks to solve some big problems, etc. But this is, you know, as exciting as it is for me, it's never going to be a million. I mean, it's going to be, we're already at the end of it. So the real vision is to have, you know, a qubit. Right now, MTJ is a good candidate because MRAM technology has evolved so well. Maybe you can have an MRAM-based computer where you have a crossbar of 1 million qubits, and maybe we have a hardware accelerator that's like a GPU that's useful for a whole host of applications. Okay, so that's the sort of tentative vision. That's the dream to go. And maybe you have a better qubit that's silicon integrable, and maybe that can go to 1 million qubits better, right? So these are the types of things that we are really interested about. Okay, so now let me show you some concrete MTJ-based qubits. How do you get that functionality? Now, this group is, you know, you're experts on spin, so I'm going to, you know, go over this quickly to show you some more results. But the idea is, as you know, may be obvious. You go to the physics of ferromagnetism, and then you say that, look, if you make ferromagnets, if there's this exponential barrier between these two ferromagnetic states, that gives me a retention time of years if I put an exponential of let's say 40 kT, right? If I reduce that energy barrier, I should get fast fluctuations. Now, this is, of course, only an approximate picture, because you could immediately object and say that, wait a minute, if you reduce that barrier, you're not going to have up and down states anymore at some point. So you can't use this Arrhenius type relationship. And you would be absolutely correct. And in that case, you would have to do a proper theory of this and see what happens. And that's what, you know, we started, you know, in the beginning. And MTJs, of course, you're all familiar. Let me, you know, skip that part. But the basic idea is maybe you have an MTJ with an unstable free layer. And if that's fluctuating as a function of time, you can have a sort of a world's smallest random number generator. And Julie Grolier and her colleagues, they were the ones, I think, in the beginning who saw the potential of such super paramagnetic MTJs, you know, a few years ago, right? So, and at that time, it wasn't really clear in MTJs whether this could be picoseconds or nanoseconds, the fluctuations. Basically, because, you know, in magnetism literature, it's really interesting that people kind of neglect the low barrier regime. They say that, okay, if a volatile magnet is as useless as anything, so we're not going to write anything, even though the theory is simple. Nobody had done it, right? And we were seeing, you know, fast fluctuations. We had some theoretical results, and then that part. Let me come back to this. And then many experiments came along, actually from Tohoku, from IBM, and now from Max Planck and JGU, that basically showing from, you know, you recognize Matthias Klaue, obviously, Gerhard Jacob, and, you know, Fukami, Jonathan Sun from IBM. They were able to use these in-plane magnets to sort of get these fast fluctuations. Okay, and those fast fluctuations in some basic circuits that modify the STT MRAM architecture. Here we have this 1T, 1MTJ STT MRAM cell. You change it a little bit and you use an unstable free layer. You add 2 more transistors, and that gives you this tunable randomness, this functionality, this ideal behavioral equation that we cared about, right? And in fact, nowadays in the lab, you know, these stochastic MTJs that Shunsuke Fukami and Professor Ono send us, we can build microsecond p-bits, which was, you know, just a few years ago, this was impossible. It was 3 orders of magnitude slower. You could only see millisecond fluctuations, right? So magnetism can be fast, and it can give you this random numbers, a million random numbers every second. In fact, we think that it could give you, you know, because these were experimentally demonstrated, they could give you 1 billion numbers every second, right? So that would be very, very interesting. Now, let me show you a quick example on how these optimization problems work and how we think about them using p-bits. And here's an example of this integer factorization as the circuit satisfiability, as expressed as a circuit satisfiability problem. Now, what does that mean? What you're seeing here is a multiplier with AND gates and full adders. This is schoolbook multiplication that all of us know. You multiply 2 numbers, you shift them, you add them, you shift them, you add them. That's what this circuit is doing. And this is in fact having your chips for multiplication. I mean, something like this is happening in your chips. But here, the catch is we're going to do it with probabilistic bits and probabilistic gates. And what happens is, in that case, this becomes this interesting circuit satisfiability problem where you can ask the circuit, what makes you, oh, okay, you can give me a multiplication A times B. But can you give me the opposite? Can I fix your product to some number like 21? And can you give me the correct answer 7 and 3 or 3 and 7? And if you do that with p-bits, this becomes a graph. It becomes this complicated 3,500 p-bit graph. And it's described by an energy. And there's an enormous amount of states that satisfy, or that it's kind of in the phase space, right? And you're trying to find that single set of numbers that satisfies this output. So from a physics point of view, this is a very difficult problem. It's a spin glass with some exponentially many states, right? And we use advanced algorithms, the things that are called things like, you know, adaptive parallel tempering, these more powerful Monte Carlo algorithms, and we solve these, you know, problems. This is a recent result where we factor a 40-bit integer, for example. You know, this number is in some, you know, I'm not going to try to attempt to read this. I'm not, you know, a native speaker of English, but you can see that this is a huge number, right? And what I'd like you to focus your attention is, you know, in 200 seconds, we used up 123 trillion random numbers. This is an integer. You know, this is actually, we used that many random numbers in 200 seconds to solve this problem. So now you see the massive need for random numbers to solve these hard problems. When it becomes very, very difficult and rugged energy landscape. And you have these replicas that are running at different temperatures and they're exchanging information. It takes a lot of probabilistic flips per second. Okay, so this is why it's so important to find good p-bits and energy efficient p-bits and so on. Now I have a few more examples too. I'll briefly go over them, but I think I will, you know, in the next few minutes I'd like to conclude. So we've gone, as I mentioned to you, we've gone beyond combinatorial optimization. Recently we've been trying to train these physics-based ML models, these powerful ML models, in the form that they weren't trained before, because our FPGAs can take so many flips per second, like billions of flips per second, flips every second. So that's why we've been doing things like this. You're thinking of hybrid computers. You have a PC, probabilistic computer, and then you have a classical computer. And then you try to your classical computer gives you your new weights, and then your probabilistic computer gives you correlations or samples. And then you go round and round, and you try to train things like handwritten digits. And in fact, you can even do, you know, classification, of course, is a, you know, tough target to beat these days. And we were training, you know, MNIST here, and we were doing this in graphs that are taken by D-Wave's quantum computers. We can talk about this in detail if you're interested. But one thing I'd like to show you is this machine was also able to generate new things, because it's a generative ML model. It can sort of from its memory, you can ask it like, give me a 9, and it would give you a 9. Give me a 4, and it would give you a 4. And these are a little bit like those diffusion models that are very popular now, that kind of start from random noise and give you some image at the end of a calculation. This is a little bit like that, where you kind of start from noise and you anneal the system, and it's going to give you the digit that you want. right? And this machine learning, we've also been applying it to, this is kind of recent and new work that we're trying to do, which is take a quantum magnet like a Heisenberg Hamiltonian and then try to solve its ground state with these Boltzmann machine or energy-based machines. And we turn that into a network, and we sort of do this variational learning where you change your parameters of the model, and that model eventually is able to find the ground state of this quantum Hamiltonian, which is of course a many-body problem, right? This has now become a matrix. It's a 2 to the n by 2 to the n matrix, and so this is another area that there's a lot of need for, both from hardware and from algorithms and theory from physics that could change this established wisdom in these fields. Now, one final thing is, qubits are intellectually interesting, but they're not the relevant benchmark, really. With all due respect, we find it hard to compare with qubits because, they're kind of very experimental at this stage, and it is understood in that field that you need millions of qubits to be able to do something valuable. So a more relevant benchmark is bits. Suppose I'm doing this MTJ-based p-bit with digital components, which is what we do in the FPGA. And what you do is you usually have a lookup table for that digital bit. You have a pseudo-random number generator privately stored in that p-bit, and then you do a comparison and you get this p-bit behavior. Okay, that looks like a digital sort of component, kind of building block. And it is tunable, right? This tangent lookup table gives you this tunability. And then you have a PRNG, and these are these acronyms for different random number generators, LFSRs and Zoshiros and things like that. But if you compare just how many transistors you need to build these p-bits, you find something striking, which is this is a transistor count for low quality and high quality random number generators done out of single transistors. This is a synthesized result, that this is what you would get if you try to build a chip today with these digital compute components. And we split them into two pieces. We say that, okay, tunable and non-tunable. So let's focus on the tunable p-bits. Even if you use a cheap random number generator, you require about 5,000 transistors just to get one p-bit. And if you use high quality randomness, which is often needed in these quantum and machine learning applications, you require 11,000 transistors. And with MTJs, you get that for like with a few transistors and an MTJ. So that's a tremendous difference. If you want a million bit P computer, well, you need 10 billion transistors just for the P bits, not for the connectivity, not for the readout, not for all the periphery. So it becomes very, very difficult. And there is, of course, corresponding energy advantages. You see that, you require 100 times more energy, and that's what becomes very difficult if you try to do this with digital systems. Now, let me give you one final comparison before, this is my last slide. And that is this, it's this important idea of a metric for a P computer. I've been saying this for a while now, that we require a lot of random numbers, but the key metric is this flips per second for a P computer, for a Monte Carlo system. Why is this so important? Well, because I told you before that for some problems, we require 200 trillion samples. So how do I get to 200 trillion? Well, make your speed fast. So imagine the clock frequency of a P computer as this flips per second number. And if that is fast, then you're going to get 200 trillion much faster. Right? So that's the basic idea. So where are we in today's computers and GPUs and TPUs? My point is we are already, so it's a busy slide, but it's kind of bear with me, that the y-axis is power consumption, x-axis is sampling throughput, flips per nanosecond. Now, with FPGAs, those field programmable gate arrays, that digital emulators that I showed you, we can already get 100 flips per nanosecond. 100 flips per nanosecond, which means that, 100 flips per nanosecond, 100 billion flips per second. So in 10 seconds, you're getting to 1 trillion. So that's a good number. And comparisons from NVIDIA and Google, these are their papers, all published data. they're bunched up around 10 flips per nanosecond. Okay, so 10 flips per nanosecond, so 10 billion flips per second. So these are incredible numbers, but that's sort of the limit of our technology. Okay, and okay, we improved it with FPGAs because we have a more specific design. GPU is designed for something that is more general. So we improved it, okay, by a factor of 10, but that's not a lot. If you do this with MTJs or with nano devices, for example, imagine 1 million MTJs that are flipping every nanosecond. Well, then you can have 1 million flips per nanosecond. Orders of magnitude improvement is possible. So the idea is, you know, with nano devices, we could have a lot of points in between what is demonstrated today to what can be projected to tomorrow. And these types of things can help with all sorts of problems in machine learning and Niskera quantum computing. And you can even define the notion of a p-bit or a supremacy or advantage. So with that, I'd like to conclude my talk, and thank you for your attention.
Thank you very much. If you guys have questions, please raise your hands or write in your chat if you like. Let me see, there's a few. Okay, let me promote Matthew in here. Matthew Daniels. I will start the questions. He will join us in a second. I have a question myself, but I'll wait until Matthew starts the ball rolling. Go ahead, Matthew.
Oh. Hi. Hey, great talk, Kerem.
Good to see you, Matthew.
Good to see you. So I had a question. You talked somewhat early on about the idea of having like and it was a theme throughout the talk, of getting to some sort of p-bit crossbar accelerator, some sort of, you know, hardware kernel based on MTJs, and to get this really fast parallel switching. And you also briefly mentioned some stuff about graph topologies with stuff like that quantum Hamiltonian had these chimera graphs, and, you know, all the D-Wave stuff is related to that. So I guess my question is, assuming we'll never, you know, build an all-to-all connected hardware p-bit system, what are sort of the what would a realistic hardware kernel look like to you? I'm not really familiar with the strategies of you know, using kernels to map onto these large graph algorithms. I don't know what level of duplication or whatever is needed, but I'd appreciate if you could comment on that and what sort of size would be appropriate for sort of the ideal kernel in that context.
Thank you, Matthew. This is an excellent point, which I briefly talked about, but really not said it loud and clear. I do agree that we're never going to be all-to-all, and this is obvious to people like Matthew, but not always clear, because in machine learning they get spoiled with these all-to-all connections. Now, this is a good example. Now, and Matthew's question is, what is the real answer is, what is the right graph topology? I don't know. I know that it is sparse. I know that, and there is this existence proof in VLSI, our computer chips with 100 billion transistors. It's not nearly all-to-all. It's very sparse. So there we found a systematic way of building complicated things out of sparse building blocks, right? Sparse networks of gates, logic gates. Here, that is something we are kind of experimenting. There is no system. I don't know the answer. That's the truth. But we know that anything that looks dense, we've always found ways to sparsify it, so long as there are p-bits around that you can use to make auxiliary bits or copy bits or shadow bits, whatever it is. So this is a good example that came from D-Wave. You know, this is an all-to-all graph, at least, you know, bipartite all-to-all restricted Boltzmann machine. And the way you put it on a sparse network is you say that, okay, I'm going to split this up into pieces and sparsify it and put it on a chip. But these things are kind of experimental right now. They're not completely systematic, and the field is looking for those building blocks, that the macros, crossbars that you mentioned, to go to large numbers. You mentioned size. I think we never run out of use cases or uses for more p-bits. You know, there's lots of algorithms that require replicas. You know, physicists love these replica-based algorithms. So it's almost like, you know, the more the better. And today we would be very happy to get to 100,000s. But maybe with MRAM and the stuff that you guys are doing, maybe it could be more. So let me stop there and maybe, yeah.
Yeah, if I could just, yeah, I don't know. Actually, that was a pretty good answer. I have some more thoughts. Maybe I'll touch base with you offline. Thanks, Kerem.
Thanks. Thank you, Matthew.
Let me get Lev to ask his question. Then I'll see when Lev is coming on. He joined us. Okay, Lev wrote something. Oh, he's
yes.
joining us in panelists. Yeah.
Okay.
Lev, would you like to ask your question directly, or? Yeah.
Hi, thank you. I actually written it explicitly, but the question is, well, first, thank you, but the question is, what are the benefits of actually probabilistic bits for factorization problems when you can just do exhaustive search? And I'm just trying to see what's the benefit of random numbers versus successive numbers.
Yes, so thank you, Lev. Yeah, so Lev catches me on this and he says that there's a much better algorithm here, which is this number is some big number, and you're talking about 123 trillion flips or whatever. Why couldn't I just start from 1 and go to square root of that number, try everything and successive division, and you can ask probably GPT to write that algorithm for you, and it'll do it in seconds. And you would be absolutely correct. In factorization, you could do this. There's a very good trial division. This is called, this idea that you expressed, Lev, is maybe you already know this. It's trial division algorithm for factorization. And it is, yes, that's true. And there are better algorithms, but this is one, right? Now, here, factorization has been for us an example of a hard optimization problem. It's a glassy, very difficult landscape for probabilistic solvers. And a lot of people, as you can see, most of this is other people. A lot of people have used this as a hard benchmark for optimization problems. So it's a very good one to compare, that you can immediately see if you've done something useful, if you improve this factorization by the optimization algorithm for factorization. But the real value of this thing is there are many other combinatorial optimization problems where you absolutely have no such easy successive trials. Because in other algorithms, you will have to try 2 to the n possibilities, which is much worse than using these annealing type algorithms. So you are correct in this example, but the use case is much more general, where there is no exhaustive search becomes exponential, not just successive integers. In that case, it becomes hopeless, really.
So this is basically kind of a toy model to test your system, not the application itself.
Yes, this is a hard problem for all these solvers. It's extremely hard. It's not toy in this context because it's 2 to the n, and n is some enormous number, 3,000. But you're right. There's another algorithm. There's something that's not probabilistic that would solve this problem. But this is very representative in optimization. We have a glassy landscape and we don't have another algorithm. In that case, you have no other choice but to use heuristic probabilistic algorithms. Thanks. Thank you for that excellent point. Yeah.
So then I have a couple of questions. Curious about. So you said that when you have this 10 to the 6 in the MRAMs bits per nanosecond, it's because I guess you have in the MRAMs you have a 1 gigabyte RAM, and then you have gigahertz type of devices, right?
Yes.
Speed of those. So if you manage to create MRAM at terahertz with antiferromagnets or altermagnets, then that would be a bit of a change, right?
It would be more than a bit of, yeah, it would be amazing. Yes.
Okay.
So, in the beginning, we were writing papers on these fast magnets, and it wasn't clear even to experts. I used to hear that, random walk is a slow process. You get a nanosecond fluctuation. With in-plane magnetism, this fast precession around the out of plane component, this shape, out of the mag field, you get these very fast kind of fluctuations. Now, if you can use altermagnetism, you know, completely new concepts, or even antiferromagnets to make this faster, yes, that could lead to a substantial change on our projections, and because the more flips are always going to be useful. These are, you know, because it's just a fundamental thing about this whole thing.
Yeah, I imagine that from the physics point of view, antiferromagnets will be challenging because you still have spin-orbit coupling scales, but altermagnets
may not have that.
You have terahertz and ferromagnetic behavior, so you know the question is controlling the domains. The question that I asked you before is a little bit to understand. Once you're looking, because you were very descriptive on saying, okay, look, we need to use this probabilistic ones for particular type of problems, or optimize these problems, and then benchmark them with others. It's not one versus another. And then for just a clear understanding, is there a way when people ask you, well, you have quantum supremacy, and that you want to have probabilistic supremacy? Is this probabilistic supremacy to what type of problems does it apply, or when do you need, even though you may not have a number of qubits needed, entanglement to solve a problem that it couldn't be solved otherwise with probabilistic computing?
So let me be, I mean, I don't want to be misleading about quantum computation, because we have seen it. I'm not just quoting others. We have seen, try to map these general supremacy type, quantum supremacy type experiments, or these gates, to probabilistic bits. And there is a mapping, but then you need exponentially many samples. It's like what they can do in 1,000 samples to get to reduce their errors in estimating that distribution. You need some 2 to the n, which is okay. So here's a set of problems where we will never, unless there's a break, unless the sign problem is solved, we're never going to. So there is that class of problems, and those problems, I think you mentioned that last time, they require this phase cancellation. There's this in the 2 to the n space. You have to cancel these complex phases. If they cancel, then we are in trouble. Then I think probabilistic falls absolutely short. And that's what they did in that experiment. They took a bunch of gates and they rotated this wave function. And every rotation, of course, involves cancellations. And that's a very difficult thing to estimate, no question. The only problem there was it isn't easy to make that useful. Why is, in that case, it was a great random number generator, but it wasn't, there's still no known use for this random sampling experiments in quantum. Now, in the case of, so that they're still looking for their, examples, and that's good, and that could be very useful. Now, in the case of probabilistic, the targets are more easily identified, but they're harder to beat. For example, take an optimization problem. Can you really solve an optimization problem with probabilistic computers faster than, or faster, better, lower energy, whatever metric that you choose? Can we beat best state-of-the-art algorithms without fixing the discussion to probabilistic algorithms? So far, I've been showing you stuff where the comparisons are always probabilistic, but in CPU. No, don't tell me what to do. Here's the problem. You solve it with your probabilistic computer. I solve it with the best algorithm I know. Can you beat me? And there, I think it's catching up. It's not, I don't think that we are there yet in any sense of the word, but we've started to become comparable, especially in these emulators. And if those emulators were much faster with magnets or with new ideas, then you could enter into regimes where you solve something faster than anybody else. And optimization is a good example, and ML is another good example where there's a lot of physics inspiration in some of these models. And but that's the honest answer right now, that we're not there yet if you compare against the best algorithms.
Yeah, exciting. Good. So thank you, Kerem. Once again, I think there are not more questions today. I mean, of course, this this crowd is not a probabilistic crowd or computing crowd, but I wanted to educate some of my colleagues to be aware of it, because some of these things, actually, particularly from the hardware point of view, is quite an important challenge that I think could be useful, particularly if you get terahertz TMR.
Yeah, that's very interesting. That would be amazing.
That would be your dream, yeah?
Right.
I would dream for many people, probably.
That would be good advertisement to your community that, please do that. And